What kind of house can survive a place where the air itself is trying to erase heat from existence? At -40 degrees Fahrenheit, the Arctic is no longer just cold. It becomes an active force. Heat is taken, stripped, stolen in seconds through a process: forced convection. When 40-50 mile-per-hour winds sweep across an open tundra, they don't just pass over surfaces. They peel away the thin molecular layer of warmth, freezing skin, and crystallizing breath mid-air. Even materials behave differently, becoming brittle, rigid, unforgiving in this environment. This environment is not just cold, it is an infinite heat sink. Any warmth introduced is immediately absorbed and dispersed into the vast, energy-hungry Arctic void. The real question isn't how to stay warm, but how to stop losing heat at all. In most human history, survival begins with fire, providing heat, light, protection, and energy. But in the high Arctic, fire alone is not a solution. No wood or fuel for sustained combustion. Even if a flame is created using animal fat or oil, it produces only a small, localized heat source. Against Arctic heat loss, it's almost meaningless. Traditional architecture fails completely here. A house built on the surface with thin walls and exposed angles becomes a liability, leaking heat. Wind creates pressure differences, pulling warmth out through microscopic gaps. A house cannot simply contain heat. It must trap, store, and protect heat from being taken. The solution wasn't better walls. The solution came from changing where the house exists, fighting the Arctic from below. They moved homes into the earth itself, sinking structures 3 feet below ground level. They exited the chaotic, wind-dominated air and entered something far more stable below the surface. Below the surface, the wind disappears. Temperature fluctuations slow, and energy loss becomes predictable. This was a shift from weather to geology. It sounds counterintuitive, but it works. Beneath the Arctic surface lies a valuable resource: thermal stability. Permafrost, frozen for thousands of years, maintains a constant temperature near 32 degrees Fahrenheit. While air above plunges to -40 degrees, the ground resists change, holding its temperature. Its immense mass makes it a thermal battery, equalizing interior space with the Earth's temperature. Even without a strong heat source, the interior remains near or above freezing. With minimal additional heat, it can rise dramatically. Survival is no longer about fighting the cold. It's about working with the planet's stored energy. Wind is not just uncomfortable, it is destructive. High-speed air creates pressure zones, pulling warm air out through even the smallest cracks. A traditional structure becomes a leaking system under constant attack from the wind. The Thule solution was elegant. Don't resist the wind. Lower the structure into the ground. Shaping the roof into a dome redirects airflow smoothly, eliminating sharp edges and vertical walls. The house stops being an object in the environment. It becomes part of the landscape. Sinking into the ground solved only part of the problem. There was still the question of structure. Without timber, how do you create a roof strong enough to hold snow and resist collapse? The answer came from the sea. A single bowhead whale provides tons of usable material. Its massive curved jawbones, often over 15 feet long, were used as primary support piers. Arranged in a circular pattern, they formed a dome, one of the strongest shapes in structural engineering. Unlike flat beams, arches convert force into compression, distributing weight evenly. The whale skeleton became a load-bearing framework, supporting heavy snow loads and resisting deformation. The ocean had become architecture. Structure alone does not retain heat. What transforms the dwelling is its outer layer, thick animal hides stretched to create a windproof membrane. On top, a dense layer of tundra sod, often 3 feet thick, was applied. This sod was not just dirt, it was a living, fibrous matrix of moss, roots, and organic material. Installed with roots facing inward, the plants remained alive, intertwining and reinforcing the structure. The house developed a self-sealing skin, a biological barrier that repaired small cracks and resisted wind. It was no longer a static shelter. It became a living system. Inside this insulated, earth-embedded structure, even a small heat source became powerful. A single oil lamp burning seal or whale fat could raise interior temperatures dramatically. The system no longer loses heat rapidly. Thick sod provides insulation, and earth provides thermal mass. The dome shape reduces airflow disturbance, creating a controlled environment where heat accumulates. The result is astonishing. Over 100 degrees Fahrenheit difference between inside and outside. This is achieved through energy retention, not production. But this near-perfect system introduced a new danger. By sealing the structure so effectively, airflow was reduced to almost nothing. Without ventilation, deadly elements like carbon monoxide, carbon dioxide, and moisture build up. The same system that preserves heat can suffocate its inhabitants. So the challenge evolves again. Now it's about fluids. Air must move slowly, precisely, without releasing heat. Ventilation shafts, entrance tunnels, and subtle airflow channels regulate this balance. Too much airflow loses heat. Too little makes life impossible. Survival becomes delicate engineering. What emerges is far beyond a shelter. It is a closed-loop thermal system. The earth stabilizes temperature, the structure minimizes exposure, and insulation traps heat. The shape redirects wind, and airflow sustains life. No fossil fuels, no external power. No excess materials, just geometry, mass, and understanding. In a place where survival seems impossible, this system doesn't fight the environment, it aligns with it. The most advanced technology isn't always the one that consumes the most energy. It's the one that understands exactly how little it needs. These structures weren't built to conquer the Arctic. They were built to belong to it. Maybe that's the lesson we've forgotten. Not how to dominate, but how to read and adapt. And survive within its rules. If this forgotten engineering speaks to you, shaped by necessity, then you're already walking the path we explore here. Shadows of Valhalla isn't just about the past. It's about rediscovering the intelligence hidden inside it. Advanced technology isn't always about consuming energy. It's the one that understands how little it needs. These structures weren't built to conquer the Arctic. They were built to belong to it. And maybe that's the lesson we've forgotten. Not how to dominate the world, but how to read it, adapt, and survive within its rules.